comparing two means or two mu values. In this topic, we will move on to working with confidence intervals and significance tests for two means. As before, we will cover the conditions and formulas respectively for population means. Given an SRS or simple random sample of size n1 for population 1 and the mean of mu sub 1 and the standard deviation of sigma sub 1, and a separate, independent simple random sample of size n2 for population 2 with a mean of mu sub 2 and standard deviation of sigma sub 2, the shape is determined based on whether or not the population distributions are normal. And if the individual population distributions are normal, then the sample mean x sub 1 minus the sample mean of x sub 2 will be normal. Otherwise, as long as the individual sample sizes n1 and n2 are greater than or equal to 30, then the sample mean x sub 1 minus the sample mean of x sub 2 will still be about normal. For the center of this distribution, the mean of the sample mean x sub 1 minus the sample mean of x sub 2 is the mean mu sub 1 minus mu sub 2. For the spread of the data, if the sample mean is less than the sample population, the standard deviation of the sample mean, x sub 1 minus x sub 2, is equivalent to the square root of sigma sub 1 squared divided by the sample size n sub 1 plus sigma sub 2 squared divided by the sample size of the second population, n2, as long as the sample is less than 10% of the population. Now let's talk about the confidence intervals with two means. The conditions for a confidence interval of mu sub 1 minus mu sub 2 are first that it has to be random. The data has to come from a well-designed simple random sample, or SRS. Condition number 2 is the 10% rule. When sampling without replacement, the population needs to be at least 10 times the size of the sample. In other words, our sample size, lowercase n, has to be less than or equal to 1/10 the size of the entire population, capital N. The third condition is that it has to be normal or large. Normal distributions, or both samples, are greater than or equal to 30. The standard error, or estimate standard deviation formula for confidence intervals with two means changes to the standard error is equal to the square root of the standard deviation of the first set squared divided by the sample size of the first set, n sub 1, plus the standard deviation for the second set squared divided by the sample size of the second set, n sub 2. While the formula for a two-sample t interval for two means is the sample mean for the first set minus the sample mean for the second set, plus or minus the critical value for the given confidence interval percentage t star times the standard error, which was explained up here. Recall that to accurately compute the critical value t star, we need the degrees of freedom. And since there are two sample populations, whereas before we only had one, we can't just subtract one from the n value to help us determine the degrees of freedom that are needed. Instead, because we're doing it from 2, we have to subtract 2 from the end after we add the two sample populations together. So the degrees of freedom is equal to the sample size of the first set, n sub 1, plus the sample size of the second set, n sub 2, minus 2. Let's try an example on constructing the confidence interval with two means. Suppose we want to compare the mean SAT scores of students from two different high schools, School A and School B. We randomly sample 35 students from School A and 30 students from School B. The sample mean and standard deviation of SAT scores for School A are 1,200, or 1,200, and 100 respectively, while the sample mean and standard deviation for School B are 1,250, or 1,250, and 80, respectively. Construct and interpret a 95% confidence interval for the difference in means of SAT scores between the two schools. The first step is to check that all the conditions are met, which they are. Our random samples are greater than or equal to 30, and these samples represent less than 10% of the actual population in each school. And the sampling method was random in both cases. So all those conditions are met. And then using the two-tailed t-distribution table at 5/100ths and a 63 degrees of freedom, and remember that the 63 came from adding the two samples together, which gives us 65, and subtracting 2 from it. So then if we actually look at a table, we can, or an online resource, we can type in the degrees of freedom, which is 63, and the significance level, 5/100ths, and calculate, and we get that the two-tail t-value is about 1 and 998 thousandths. So that's what we have for that critical value. The next step is to identify the necessary values to use in our confidence interval formula. So for our x sub 1 bar, or our sample mean for our first set of data, we have 1200, and then we also know its standard deviation, S sub 1, is 100. So we know that x bar sub 1 is 1200, and we know that S sub 1 is 100, and we know our n value for school A is 35 students. So we have all of that data so far. Now let's look at school B. School B, they randomly sampled 30 students. That's our N2. And the sample mean and standard deviation of school B are 1250. So that's our x bar sub 2, or sample mean sub 2, and 80, which is our S sub 2. So we have all of those values, and then the last thing that we just calculated was our t star value, which is 1 and 998 thousandths. And now that we've identified those key values, let's substitute them into our equation and simplify. So we have 1,200 minus 1,250 in parentheses, plus or minus our t star value of 1 and 998 thousandths times the square root of 100 squared over 35 plus 80 squared over 30. And if we substitute these values into a calculator, we see when we do 1200 minus 1250 plus 1 and 998 thousandths times the square root of 100 squared over 35 plus 80 squared over 30, we get negative 5 and about 366 thousandths. And when we evaluate the formula with the subtraction sign in between, we get negative 94 and about 634 thousandths. So that makes our confidence interval for our 95% confidence interval for the difference in means of the SAT scores between the two schools to be from negative 94 and 634 thousandths to negative 5 and 366 thousandths. And now we can interpret our results. We are 95% confident that the true difference in means of SAT scores between school A and school B is between negative 94 and 634 thousandths and negative 5 and 366 thousandths points.